Good morning, good afternoon, and good evening, everybody, and welcome to another session of Expand Your Horizon. Together with us today is Ning Li, the co-founder and CEO of NovoLINC. Hi, Ning. Good morning to you.
Hi. Good morning, good afternoon to your team in the global locations, and it's an honor to be here. Thanks for inviting NovoLINC and myself to be part of the conversation.
Yeah, thank you very much for joining, and thank you very much for making the effort to tell us the story of NovoLINC, which is very exciting. And we'll talk today about data centers and AI and how much energy these things consume and how NovoLINC was founded to solve this challenge. But maybe before we do that, Ning, would be great to get to know you and your story before you founded NovoLINC. So maybe you can take a few minutes and share with us your journey.
Yeah, absolutely. Let me start with talking about the NovoLINC, which is a startup company headquartered in Pittsburgh, Pennsylvania, United States. We have innovated nanomaterials that really solving the most urgent issue the AI data center is facing, which is chip cooling. We are setting a new standard for the thermal interface management. So hopefully the takeaway or the punchline for this discussion is that every chip on Earth relies on the layer no one talks about or yet, and then we made it 10 times better. So it is a technology that's funded, sponsored by National Science Foundation and the U.S. APAI Cooler Chips program, and it is also funded by great venture partners, including M Venture, Foothill Venture, and the TDK Ventures. So under the big picture that the AI data center are in need of better solutions for chip cooling, NovoLINC, with the record-setting thermal performance, is coming to help the ecosystem, enables massive energy and cost saving. And we are gaining rapid traction from top-tier customers. And then the company is led by a world-class team, and we have exclusive IP protection, and also the whole technology is built to scale. So for myself, I'm a material scientist by training. You can see my career spans at 3 major phases, and typically education foundation. So I counted like I spent 22 years going through school and getting my PhD from Rice University in Houston, Texas. And later I also obtained my executive MBA. So hopefully with AI, I think the education journey for future scientists, engineers will be shorter. But what I had has built a great foundation. And then I spent 18 years working for one company, Seagate Technology, leading product development and advanced technology staging. You see there are 3 logos of Seagate that really reflects over the years how a company evolve and then rebranding itself from the internet era to mobile cloud era, now into the AI era. So in 2016, after I talked with my management, thinking about the future for any hardware company is actually to bring AI into the system, and then that's the most important value proposition. I moved to Pittsburgh and then started my 9 years journey till this day as a serial entrepreneur. First, I'm a co-founder of AI platform company, Petrum, and then we worked on platform framework and the vertical solutions for industrial and healthcare. What we worked with cement companies, oil and gas companies, and healthcare institutions. Later, I joined another late-stage startup. It's a medtech company called Genesis MedTech, focusing on providing AI to surgeons in post-op and intra-op. And I think the most exciting moments comes in 2024, which I co-founded NovoLINC with Professor Shen and Dr. Ray Chen, who's a postdoc at CMU. So I think this marks a very significant journey that we will bring a solution to the AI industry. And also in 2019, I also joined Foothill Venture as a venture partner. So at this stage, I think I'm bringing to the table 18 years of large corporation R&D experience, launching products overseas, and then entrepreneurship experience, funding companies, raising hundreds of millions of dollars, growing the team to over 100 people in a short 18 months, and then also experience in venture investment. So hope all this will come into making NovoLINC a great company.
So, probably if you go back one slide, kind of like the perfect combination of a very, very deep scientific experience through your education, working in one of the largest technology companies in the world, founding a few startups, and working as an investor. It's kind of like the perfect match to a serial entrepreneur. Would you feel comfortable telling us a little bit outside of the professional world, kind of like, a little bit more about you outside of work?
Yeah, absolutely. Outside of work, I enjoy spending time with my family, outdoors, hiking, biking, skiing in the winter, and I like gardening. And yeah, I think that's kind of the balance of work hard is that you also need to enjoy life in very high intensity.
Any specific hike that you've done recently that you would recommend to put on our list?
Yeah, so there's a couple of things that last year I had the pleasure to finish the Tour de Mont Blanc trekking, which is over 100 miles, 10 days journey across the Alps mountains. So that was very refreshing, and that is definitely one highlight of my recent adventures.
Yeah, I heard a lot about that hike. It's like quite intense elevation, right, during that hike.
Yeah, I think the most important thing is you need to plan well and have enough training. Kind of like it's the protocol of doing anything successfully. A team work together, put together a great plan, and then you go through almost 9 months scheduled training to get yourself ready for that challenge.
Amazing. And before we move to talk in more details about NovoLINC, one question that I ask every guest: what are the two things that if I Googled your name, or today if I ChatGPT your name, what wouldn't I find about you?
Yeah, ChatGPT is actually amazing that I never put in any public record that I went to the TMB tool, but then ChatGPT knows it. So, but there are things definitely that I'm kind of glad to share. The love of nature starts from during the senior year of my college. We actually went on exploration to explore the headwater of Yangtze River in Tibet. So me and my husband, at that time was my boyfriend, was in the team. So that's definitely a very memorable journey. At that time, that peak is still a virgin peak that no team has summited before. And I also like writing. I like art. I co-authored a book. I write in Chinese. The book is called Stone of Hope. It's a story of a master sculptor for the Martin Luther King Memorial in Washington, D.C. And so if you ever want to know more behind the scenes story about that memorial, yeah, we can have some good fun time to chat about it. I also like to do nonprofit organization work. I'm a proud mom of Eagle Scout, and I also sponsoring the annual RISE 360 undergraduate global health technology design competition. So there is a Crystal War Award aimed at awarding innovation in material science and also in digital health.
Amazing. Thank you for sharing that with us.
And I also have a couple slides to mention about hard disk drive industry, because every time I look back at my 18 years journey at Seagate, I feel grateful about all the great training and the great opportunity to lead advanced technology, advanced product. So people may not know that hard disk drive is such competitive industry that over the years, over 200 companies entered the space. Only 3 survived to these days. So currently, there are only 3 companies in the whole world can produce hard disk drives, which is Seagate, Western Digital, and then Toshiba. So when I look at it, is a smart robot knows where to find a single bit from a total of 250 terabit, which is packed in that case you see on the screen in 4.5 milliseconds. And then the whole pack consumes less than 12 watt power. And amazingly is that you're able to get $30 per terabyte economy out of it. So it is definitely an engineering marvel. It's when the recording head flies over the recording disk, it is like flying an airplane of 747 at a 30 centimeter clearance. So that's kind of the challenge the industry has been working on over decades. And then a couple of takeaways. The industry had a log linear curve, just like a Moore's law. In the industry, we call that Kreider's law. It's named after Seagate CTO, Dr. Kreider, who was a dean at CMU at one time. So basically, the story is that over the last 60 years, the recording area density has been growing exponentially. So you will see several S curves representing the technology migration from one generation to the other. And another amazing fact is technology is a major deflation force, right? So we heard about the world efforts in fighting inflation, and then kudos go to all the engineers in the world to make things happen. And you can see over the last 70 years, the cost of storage, along with other computer memory, has been on a log linear cost takedown trend. So that is pretty amazing. So with that, I'm ready to switch gears, talking about the data center and then the opportunity NovoLINC is providing. A typical hyperscaler data center, we call that AI ready for this year. How does it look like? So it needs land, it needs water, it needs a lot of power, and then you need a great construction, and then you start to putting in AI equipment in there. Those are typically AI servers, which composed of CPUs, GPUs, photonics, data storage components, and then the cooling system. So the number listed on the right is one kind of scenario that ChatGPT summarized for a typical size data center per industry standard. And the amount of power it consumes is astonishing, and it's can be ranging from 3 to 7 terawatt hour. And then the amount of water consumes is in the 100 million gallon per year. So it is the global data center is operating in such a large scale that the sustainability of it needs to be taken serious consideration about.
And the water, and we'll talk about it later, but the water and the energy is primarily for cooling.
Yes, so there's a breakdown on the right-hand side chart. Currently, 30 to 40% of the total energy are spent on cooling. That's why you will hear Jensen from NVIDIA talking about the limitation for the GPU is energy bonded. the industry is targeting at reducing the energy consumption for any other components and then trying to put it more into computing. But of course, high power computing has its own challenges we will talk about in the later slides. So on the left side chart, it's an old chart, but I think it represents very well that the global data centers consumption of energy comparing to the magnitude of energy that a single country is consuming. So and then the number is also growing at 20 to 30% CAGR. So it's a very serious challenge that our technology is looked into to help to resolve.
Yeah, I'm guessing this number is getting bigger and bigger, and the plans, at least the public announced plans to invest in data centers, what we hear from the Microsoft, the Googles, the Amazons of the world, we're talking about, I don't remember the exact number, but we're talking about 60, 70, $80 billion per company per year in the next 5 years only to build the infrastructure for AI.
Exactly. And then AI is being integrated into the society, into everyone's life, everyone's work. So the moment, I think a lot of people are referring that to the moment of internet. So we're just at the starting part of the journey. So thinking about why solving cooling is so critical, and the server rack packed with GPUs produce as much heat as a bonfire. That one GPU currently is operating at 1.2 to 1.4 kilowatt of power. And then to make the whole system work, that's the amount of cooling that went into the data center design is at a very high percentage. So 30 to 40% of data center energy, we call it wasted on cooling, but it's necessary. It's not wasting, it's to keep it running. But the IT folks definitely wish that more energy was spent on computing instead of in cooling.
For the people in the audience that are not familiar with the architecture of a data center, let's try to picture that. So imagine your laptop, or imagine your desktop computer. You know that it has a certain processor that does all the computing. And my Apple Mac is currently, I can hear the fan working because it releases heat that the processor is generating. And you probably saw on your desktop, when you open it, you saw fans inside that, because those processors generate heat, this heat need to be released to the ambient temperature. So, and this is only one computer. Now think about thousands of these processors, and in the industry we call this processor GPUs or CPUs. It doesn't matter the name, but imagine GPUs and CPUs. These are all the devices that are making the computer work. And you put these on trays, and you put these trays in a closet. And what you see on the picture here on the left, below the bonfire, is basically 1, 2, 3, maybe 10, 20 closets filled with thousands of these processing units that generate a lot of heat, right?
Yes, exactly. I think you summarized that very clearly. And then that amount of heat needs to be dissipated away through the downstream thermal exchange system. So the industry is facing a pivoting point that direct liquid cooling in data center is taking place, replacing the traditional air cooling. So when you compare the heat resistance of air, which is one of the worst, and then it's several tens of times higher than liquid. So that's why this technology transition is happening in the data center infrastructure. And then this chart actually exactly picturing what you were describing. So from the data center chips or even any CPU, GPU, XPU that's in the PC, the power density is increasing exponentially. So we talked about the Blackwell B200 announced early this year at CES, and those were performing at 1.2 to 1.4 kilowatt. And then the industry roadmap is driving to increase that to 4 to 5 kilowatts in the future. So you can see it's the trend is very clearly defined.
Yeah, and again, just to help people understand what we're talking about, imagine you take a closet and you put, I don't know, 20, 30,000 processors or GPU in that closet. Up until a few years ago, these things had a certain power consumption. But what happened in the last 10 years and what will happen in the next few years is that this power consumption in the same closet will increase by 4, 5, 6, 7 times, which means also that the heat that this closet is emitting is 4, 5, 6, 7 times more than it was just a few years ago. And correct me if I'm wrong, Ning, but we reached a point that today, even if you put a dedicated air condition just on that closet, air is not sufficiently good in releasing the heat that those closets today are emitting, correct? So we reached the limit of what air conditioning can do.
Exactly. And then the reason is that you just think about the closet is wrapped in the Canada Goose jacket that the heat just cannot coming all the way from inside to the outside. It's called thermal interface challenge. So to solve that challenge, we just talked about how the cooling system are becoming more efficient. And the industry is quickly adopting direct liquid cooling with microchannels created in the cold plate, and then driving liquid through and then taking heat away from the chip.
It's kind of like a car radiator, right? You have a liquid running on top of the plate, and the dissipate heat from the plate to the outside environment.
Yeah, it's a great analogy that the car it's a liquid assisted air cooling because you still depend on the air cooling, and then you have liquid circulating in there, and in the data center, so that the liquid is circulating with further HVAC heat exchange settings in the chillers. Basically, it's called chillers in the backend side. So so we are talking about the transition from air cooling to liquid cooling, and the liquid cooling also have single phase and then 2-phase liquid cooling. So those are in this trend that innovative companies are driving solutions for. So this graph is telling the story is that when the heat sink, the one on the top with the microchannel with the blue fluid running through, is improving for the last 5-10 years. It is making the thermal interface material, which is the orange in the chart here, that was sitting between the chip and the cold plate of liquid cooling. So the thermal interface right now is the critical bottleneck.
So what you're saying here basically is that as the cooling technology became better, the bottleneck for releasing heat from the chip is now the material that connects between the chip and the plate, And this is what we're trying to solve with the NovoLINC new technology, right?
Yes. So ineffective thermal interface material, you can just think about it's your Canada Goose jacket. You can wear that and you can go to North Pole and then still keep yourself warm because that thing is keeping the heat dissipating away from you. So what the chip needs is the opposite. It doesn't want the Canada Goose in between it and the cold plate. It wants the least thermal resistance in between. So NovoLINC's breakthrough comes in. We are providing a nanocomposite layer that will transfer the heat 10 times more efficient than the current industry standard, which will enabling the chip to be 5 to 10 degrees cooler instantly. Our work is published on Nature Communication, and then it is setting an industry record. So we talked about the team, but what exactly the form and shape does it come from? You will see a lot of different materials being used. Solder is a very typical one. It still has the best performance within the semiconductor industry packaging. But it is a metal joints and needs to facing the challenge of thermal stress and then potential cracking with the chip warping. So NovoLINC's nanocomposite material is performing 2 to 3 times better than solder. So the graph is plotted along axis. Down there is called thermal resistance. It's in log linear scale, and then it is the lower the better. You can see the air is off the chart just because air is really a great insulator. So if we put on the log scale, looking at how the NovoLINC is outperforming other existing solutions, the typical ones including thermal grease, they are paste-like, and the thermal pad, they are rubber-like sheet that is easy to be deployed on the chips. So those materials has been there for decades, and then they have reached the S-curve of their technology potential. So it is breakthrough like NovoLINC that is coming to bring the chip cooling into the next level.
And Ning, just for me to get a sense, what's the thermal resistance of water? Like if you could cool with water, obviously you can't because water also is electricity conducing material. But what is the thermal resistance of water?
Yeah, there's a lot of different liquid. I think they were in the tens. The numbers are in the tens region.
Okay, so your composite material has a thermal resistance that is even lower than water or fluorinated liquids.
Yes, I think the liquid, including water, they range from a single digit in the semiconductivity to tens of the semiconductivity.
Understood. So your thermal material is even better than if we could sink the entire chip in water and get the water dissipate the heat from the chip, right?
Exactly, because our material is metal based. So metal has a much better thermal conductivity than the liquid. Another key challenge that we are helping to mitigate is the dynamic warpage issue that the chips are facing. So the chips are getting larger in size, and then there are chiplet design architecture being proposed. And then within the chip manufacturing, the different materials being used is creating a thermal coefficient, expansion coefficient mismatch. And then it's causing the chip will be flex under the heat. It will bend if you look at that under the microscope. So the traditional materials cannot adapt, and then leading to gaps. And then once there's voids, gaps, becomes available at the interface, the thermal resistance just increase. NovoLINC material is very flexible, very adaptive, so it really mitigates the dynamic warpage issue.
And for people to get a sense of, here you're talking about the size, so it's exactly what I wanted to ask. What's the size of those chips?
Yeah, our solution comes in different sizes per the chip requirement. So we will dice and package the material so that it matches the dimension that requested by the cold plate company or by the semiconductor company. So our solution right now has the industry lowest record. The thermal resistance is at 0.7 millimeter square Kelvin per watt. And it provides better thermal performance. It demonstrated improved reliability, and then it solves the dynamic warpage challenge, and then it will save cost for data center operators.
And in terms of size, people see something here, but the cold plate that we see is what, like less than 1 millimeter in size, and those little spikes in your material, they're like nanometer spikes, right?
The cold plate right now depends on the GPU size. You may hear 70 millimeter by 70 millimeter or 30 millimeter by 30 millimeter, depends on the size of the GPU, the CPU, or the XPU that is produced by world-leading companies. And then for our materials, you can see the nanowires there. They are in the, we call that the nanowires because they are in the nanometer scale.
So the width of these like nano hairs is like even smaller than the width of my hair?
That's right. And then the density of the nanowires and then the diameter of the nanowires, the length of it are all customizable. So it is a great platform technology that can be tuned in to solve specific requirement our customers would propose.
Amazing.
So talking about how the 10x better performance would translate into power saving opportunities and economic opportunities. So putting in the assumption that 10 cents per watt, looking at 2027 of the global data center capacity, if every single chip goes into the data center uses NovoLINC product, it will create 31 terawatt hour saving. And then that number will grow at a 20% CAGR. So by 2030, so that saving will double. And then we can put that in a perspective that, say, we talk about enabling a nuclear power plant and 66 terawatt hour is worst output of several 5 to 8 normal size nuclear power plant. So basically, a nanostructured thermal interface material does provides the power of the nuclear energy in that magnitude. And if we transfer that into, we look at how much energy does each state consumes. We pick typical Pennsylvania, that's where we are in. Texas, that's where the Stargate projects that is primarily located. And then California, that's a lot of the hyperscaler and headquartered in. The saving provided by NovoLINC can power those states for months. And then if we look at the AI data center, the energy saving we are providing can actually worsen the whole energy consumption for those data centers for years. So basically, you just think about when a new data center uses our technology, they basically get a free power for a year or two, that's the amount of impact and then saving, and then also the benefit to the sustainability of the AI data center development.
So if we think about the number that you shared with us earlier, that every data center on average spends 30 to 40% of its OPEX on cooling. If that data center switch from standard materials to NovoLINC materials, this 30 to 40% would go down to what?
It will go down by 30% in the cooling efficiency for the chiller side.
Does this mean that 40%?
Yeah, so it would
goes down to 30%?
Yes, 40% reduced, go down by, yeah, exactly, go down by 30%.
Yeah.
That's
so
the amount of saving.
27, 28, yeah.
Yeah.
That's massive.
Yes, yes. Of course, it's a moving target because all the technology stakeholders are working on towards driving down that 40%. So with direct liquid cooling and the data center is in hybrid mode with both air-cooled server and direct liquid cooled server, and so that number is a moving target between 30% to 40%, but we are definitely working on making it increase by another 30%.
So so even if a data center tomorrow switch to liquid cooling, and they will take down their 40% OPEX to whatever, 25%, you can even take this 25 down by 30% using your material.
Exactly.
Wow, amazing.
Yeah. So it's not only limited to data center. The some interface material is required in all industry that generates heat. So you can see automotive industry, consumer electronics, telecommunication, medical devices. So there's actually no limit for NovoLINC solution to penetrate into those industries once there's thermal issue becomes dominant, that they need a new solution. So we're going back talking about the data center, the ecosystem. It is an ecosystem that we are working with all stakeholders at this moment. We're working with major semiconductor companies, the hyperscalers that who runs all the global data center and AI data centers, and then the data center server OEMs, and the infrastructure ODMs, and then there's cold plate manufacturers. So we are bringing the benefit, and then we'll share that with all stakeholders in the ecosystem. So let me talk about the world-class team we have. My co-founders are Professor Shen with MIT PhD, and then he's a full-time professor at CMU, and then now he's joining NovoLINC full-time as a CTO. And then the co-founder Ray was a postdoc at Shen's group, and then currently is a VP of product. And then we have Victor that's in charge of our business development. Bob Winner, with 40 years experience in IBM, Western Digital, Seagate, is a technology veteran with experience running the CTO's, managing the CTO's office, managing the global equipment at Seagate. So Bob is in charge of NovoLINC's scale up. And then we also have serial entrepreneur like Dr. John Watkins, who's an expert in electrochemistry. And then we also have a group of dedicated employees that's not listed here in making possible the great technology. And we also want to mention the support we are receiving from world-class investors. Ilya from M Venture, Eric from Foothill Venture, and Tina from TDK Venture. We also have advisors who are leading academic researchers in heat transfer, and also ex-CEO that has experience in scale-up, startup into large scale. So we are very lucky to be at this junction of AI movement. And then we are very proud in presenting a technology breakthrough that will make global AI advancement sustainable.
Well, that's quite a presentation. Thank you very much, Ning. This was very insightful. Couple of questions that are coming from the audience, and I'd like to discuss them with you. The first question is around reuse of heat. Okay, if the GPUs are generating so much heat, one of the areas that could be a solution is to somehow use this heat and then do something with it, either warm the water or create energy or convert to electricity. So can you share a little bit what's the current practices around heat reuse, and why don't we see it happening in greater capacities? What are the limitations, and what do you think will happen in the next couple of years in the ability to reuse heat from data centers?
Yeah, so that is a broader topic outside our company's focus. But when we go to the industry conferences, for example, the UPskillng Innovation Summit every year in the spring, and then there are sessions dedicated in discussing the recycle of the heat that's generated by the data center. And then because they were using water for the downstream heat exchange, so the opportunity of recycle those energy back to warm up the water for community usage, and then those are definitely there are ongoing efforts in that space.
Yeah, from the little that I know, because we have done some work on data center cooling as part of Orbia Ventures, is that it looks like there's a lot of energy that's coming in the form of heat, but making use of that heat is not very straightforward. So if you have like a nearby city, and you want to warm the water to be used in the winter to warm up the city, then this is a straightforward solution. And there are actually cities in Europe that are already doing that, leveraging heat from data centers. But in reality, the temperature differences, you mentioned 5-10 degrees, when you take this temperature differences and you try to create electricity or to do something more efficient than just heating water, it's not a very easy solution. Okay, and then if you heat the water during the winter, what do you do with the heat during the summer? So it sounds like there's a lot of energy to be leveraged, but it's not that there is a wide solution that is available for all kind of like setups on what you want to do with that excessive heat.
That's right, and then there's a lot of constraints, seasonality, and then the efficiency. But I'm sure that it is a topic that people have been taking that seriously, that we've seen that being brought up in different industry forums.
Yeah. Another question is around superconductors. Again, I don't know if you have a point of view of why superconductors are not used more extensively in data centers, or is it a technology barrier? Is it a cost barrier? So why superconductors are not more commonly used?
That's a great question and a very sophisticated question that actually say what is the heat transfer requirement for supercomputing or quantum computing? Yeah, those are beyond our immediate research topic or our product outreach, but those are really directional views that we will need to work with, partner with the stakeholders in that space to understand their requirement. So currently they're not our immediate focus yet.
Right. And I think the question was talking about superconductors, not supercomputing, like superconductors as a concept to replace potentially GPUs in some areas. Is that a relevant domain or not a focus of NovoLINC?
It's not a focus. Certain technology take years, decades to enter feasibility or commercialized stage. Like for example, the PhD topics we are researching on took 10 years. When I entered the industry, it became a reality 10 years later. So the superconductor, there are a lot of challenges for its commercialization, for its productization. So that's not yet a focus for us.
Yeah. And maybe thinking about the future of NovoLINC, and another question, it seems like there is a big problem, cooling and removing heat. It is a big problem and a big market. And you have the right solution. What are the 2-3 things that you think you need to focus on to make NovoLINC a success?
Yeah, I think customer success is our success. So one of our biggest focus is on working with our customers, addressing the pinpoint at the time, at the schedule they define, at the requirement they define, and then at the scale they would like to launch. So definitely working closely with our partners, customers is a major focus. The second one is with the scale up of the technology and have the manufacturing capacity scaled up according to the customer pool. So that is a major focus as well.
Yeah. And speaking about customers, can you share whatever you can share about current trials, current tests that are undergoing, and what do you hear from your customers on your technology and its ability to become an integral part of the data center architecture?
Yeah. So first, when you have an industry record performance, and a lot of customer is working on validating that, and then having the metrology be able to test something at a world record, it takes a lot of engineering efforts. So we have great customer support from both major semiconductor companies, major hyperscaler, and major cold plate manufacturing, major ODM and OEM companies. So we have received the customer great feedback that they were able to see, for example, in the cold plate space, by using our NovoLINC's team comparing to the existing benchmark material, it lowers the temperature by over 12 to 13 degrees. So that's a very significant improvement they are observing. And we also have customers put our material in the XPU, in the new generation XPU, and was able to demonstrating the 3, 5 to 10 degrees of improvement depending on the power density, because the improvement is a function of the power density. The higher your power density, the more benefit you're actually seeing from the NovoLINC product over the existing solutions.
And in terms of production, can you tell us a little bit how these plates are being or how these nanostructure are being produced? Like how do you actually produce them?
Yes, currently they are all, our company's operation is in Pittsburgh, Pennsylvania, and so it is produced in Pittsburgh, so made in Pittsburgh. So, and then we have Bob, our COO, is leading a scale-up plan and with manufacturing partners and working with our customers in designing equipment, automation to make this material available for the customer. So there's several advantages of our solutions. We talked about the thermal performance. We talked about improved reliability. The reworkability and the serviceability of our material is also a great advantage. And that can potentially reduce the field service burden and reduce the rework cost. So our partners are seeing the value of our technology from different angles. So when NovoLINC's team makes the chip running cooler, you can either have the chip running at a higher performance level, so you have a gain in performance, or you can improve your reliability. So there are statistics from semiconductor industries say every 1 degree above the specification will reduce the failure potential by 50%. So you just think about when we are able to make the semiconductor chip cooler by 5 to 10 degrees, that transfers to enormous amount of benefit for chip performance and chip reliability. Yeah.
And in terms of the actual material and process to produce those thermal interfaces, can you tell us a little bit more how you actually, like, what materials are used and how do you actually do you produce them like in large batches and then you cut them, or you produce the mini size at the outset?
Yeah, we have a process, and that is also protected by the IP. So our IP portfolio covers the materials design, the application, and then the manufacturing process. It is based on a continuous manufacturing process that you can dice and package into individual smaller sizes according to the chip design, and then or into a large. I mean, we've seen trend of larger form factor requirement from the chiplet design, and then from the larger XPU architecture roadmap. So our manufacturing is providing the flexibility that we can work with our end customers to decide what is the best way to integrate into their process and into their supply chain.
Yeah, but essentially, it doesn't require any architecture changes or system changes to the way that currently racks and servers are being produced, right?
Exactly. It's kind of plug and replace the existing solutions. So the switching cost or the setup cost is actually is very, very low. So that's also another beauty of our innovation. It's a cost competitive manufacturing, and it provides solves all the pain points that the customer have in performance, reliability, serviceability, reworkability, and then we also will be a cost effective solution.
Yeah. And probably we have time for one last question. So people were raising the topic of immersion cooling, single phase or two-phase immersion cooling. You and I discussed it a couple of weeks ago. What are your thoughts on immersion cooling, and will it gain traction as a potential and valid cooling solution in the data center industry?
Yes, so NovoLINC is part of the OCP startup membership circle. So OCP is the Meta's Open Compute project, which has its great platform talking about all the technology trend. So immersion cooling is a big topic there. And then I think the outlook is it is 5 to 10 years down the roadmap. And then once you were in the immersion cooling space, there are different architecture. And then some of them are teamless, some of them will still need an effective team. So our company, the experts in our company are actively participating into the immersion cooling working group at OCP, and we will have more to share through LinkedIn post or through the OCP work meeting for the advancement in that space.
But independent of NovoLINC, do you see immersion cooling gaining a significant market share of the data center cooling market? I have a point of view, but I wonder what you think.
Yeah, I think it is 5 to 10 years on the roadmap, and of course, and then the roadmap changes really depends on certain key components in the system becoming available or become non-available. So there are definitely a major milestone needs to be achieved before the technology become mainstream. Yeah.
At least what I hear from people active in the cooling space is that some pilots were not extremely successful. It's quite messy to have the entire rack sunk into a dielectric liquid. So there need to be, it's definitely going to be part of the solution, but for it to be to gain significant market share, there need to be some significant developments to remove some of the difficulties of working with liquids and having full computers sink into those liquids.
Yeah. I mean, there's definitely a lot of technical challenges there, and yeah, but sometimes you just cannot be the magnitude of challenge. It can be resolved by innovation, so it's hard to predict. And but we definitely know that the industry is just taking adoption in a large scale for the direct liquid cooling. And then with NovoLINC, we will benefit and then enhancing the lifetime of the direct liquid cooling definitely for a long time to come.
Yeah. Well, Ning, unfortunately our time is up, and I want to thank you for joining us today and sharing with us the amazing story of NovoLINC. We wish you all the success in the world, and we hope NovoLINC will be a successful company. So thank you very much for being with us today, and I'm sure we'll keep in touch.
Yeah, thanks for inviting us, and we look forward to be partners along the journey for the AI data center cooling.
Definitely.
Yeah.
Thank you very much.
Thank you.